Welcome to video 2 on mathematical induction, and we're going to do 3 examples in this video on proving inequalities and properties using mathematical induction. So on example 3 of this lesson, we're going to prove the inequality by mathematical induction for the indicated integer values of n. So you are going to prove that x over y raised to the n plus 1 power is less than x over y raised to the nth power for all n values that are greater than or equal to 1. We have the caveat here that your x is between 0 and y. So x is not negative, and your numerator is a number that is less than your denominator. First part of this, nothing changes with our process. We have to prove the base case. So when we prove the base case, we're going to let n equals 1. So this means x over y is raised to the 1 plus 1, and that needs to be less than x over y to the 1. And this is a true statement. It is a true statement. We have proved the base case is true because x over y raised to the second power is always going to be less than x over y to the first. Why is this true? Let me give you a concrete example. And again, this is an example just so that you understand why this statement is true. The example doesn't prove that it's true. If we take a simple fraction where the numerator is less than the denominator, let's take 1/2. 1/2 to the 1 plus 1 is going to be less than 1/2 to the 1 because when I take 1/2 squared, it yields 1/4. So as you take powers of the denominator, that's actually going to lessen your fraction. So something raised to the second power is always going to be less than that fraction raised to the first. My base case is true. So now for my second step, we're going to make an assumption. We are going to make an assumption that if I input k for n, that x over y raised to the k plus 1 is less than k over y to the k. This proof is just a hair different. Couldn't I multiply both sides by 1? Well, I'm going to multiply both sides by x over y raised to the first power. Why am I doing this to prove that k plus 1? Because by using properties of exponents, I have x over y raised to the k plus 1 plus 1. And that is less than x over y to the k plus 1. So part 3, if I compare that to the original, I have shown that k plus 1, when inputted into the original inequality, is less than x over y raised to the k plus 1. So k plus 1 is k plus 2. X over y raised to the k plus 2 is less than x over y raised to the k plus 1. So my original x over y raised to the n plus 1 is less than x over y raised to the n for all integers n is greater than or equal to 1. Example 4, we're going to prove the following property for all positive integers n. We're going to say that a factor of n cubed plus 5n plus 6 is 3. Again, let's prove the base case is true. When n is equal to 1, I input 1 into n cubed plus 5n plus 6, and that yields 12. 3 is a factor of 12, so the base case is true. Assume 3 is a factor of inputting k into that formula, k cubed plus 5k plus 6. Third step, we have to prove that if we input k plus 1, that 3 is a factor of k plus 1 cubed plus 5 times k plus 1 plus 6. So I have a little bit of math to do. I need to write out k plus 1 3 times, and whether you factor it out by foiling it or whether you use binomial theorem, okay, so I factored it, k plus 1 times k plus 1 squared is k squared plus 2k plus 1. And then when I distribute, I get k cubed plus 2k squared plus k squared plus 2k plus 1. When I distribute the 5 over the k plus 1, I get 5k plus 5, carry down my 6. And again, you could have used binomial theorem to expand it, but you should get k cubed plus 3k squared plus 3k plus 1 plus 5k plus 5 plus 6. Well, if you've noticed the pattern of mathematical induction, somehow or another, we need to get k cubed plus 5k plus 6 out of this, because then I know that that portion is true. So I'm going to reorder my terms. I am going to reorder the k cubed, then the 5k plus the 6, leaving me with the terms 3k squared plus 3k plus 6 when I add the 1 plus the 5. And now, since we know that k cubed plus 5k plus 6, we've assumed that 3 is a factor of that term. When I factor out a 3 out of the second portion of the term, I now can conclude that I know from assumption in part 2, 3 is a factor of k cubed plus 5k plus 6. The second term is 3 times k squared plus k plus 2, so it is a factor. Therefore, 3 is a factor of n cubed plus 5n plus 6. And last but not least, for example 5, we're going to prove that the following property is true for all positive integers n. We're going to say that a plus bi raised to the nth power and a minus bi raised to the nth power are complex conjugates for all n greater than or equal to 1. The base case is kind of like in the duh category. A plus bi to the first, and the first is not even needed, and a minus bi to the first, those are complex conjugates by definition. Therefore, the base case is true. We are going to assume that a plus bi to the k and a minus bi to the k are complex conjugates. This means if I would take a plus bi times a plus bi times a plus bi, however many k terms, it's going to yield some type of complex number c plus di. And when I take a plus bi to the kth power, it's going to yield some complex number c minus di. So let's go to the third. We need to prove that k plus 1 is true. So if I have a plus bi raised to the k plus 1, can't I think of that as a plus bi to the k and then a plus bi to the first? Because by power of exponents, I have the same base. I would add the exponents k plus 1 to get k plus 1. The same thing is true for a minus bi raised to the k plus 1. I can think of it as a plus bi to the k times a minus bi to the first. Well, we made an assumption from step 2 that a plus bi to the k is some complex number c plus di, and a minus bi to the k is some complex number c minus di. So then, if I FOIL those out, I get ac plus bci plus adi plus bdi squared, and then you see the work for a minus bi times c minus di. I get ac minus bci minus adi plus bdi squared. And then what I did is I reordered my terms, remembering that I squared is negative 1, so I get ac minus bd. And then when I group bci plus adi and pull out an I get bc plus ad. And if you notice, ac minus bd plus I times bc plus ad is the conjugate of ac minus bd minus I times bc plus ad. So a plus bi to the k plus 1 and a minus bi to the k plus 1 are complex conjugates. So by mathematical induction, a plus bi to the n and a minus bi to the n are complex conjugates for n is greater than or equal to 1. So please see page 90 of your text for more examples, and your learning opportunity number 2 is to attempt page 592, numbers 23 to 35 odd.